Good afternoon. Welcome to lecture 71 and 72 on thermodynamics of materials. We will actually take up from where we left off last class, problem 6, assignment number 7, which will continue. And problem 6 we will also continue. So actually we started this problem and introduced the problem. So you can read the problem given in the alongside, and the solution we started, I think. Okay, so relevant, just I am going through this quickly. The relevant reaction is, this is the whole process. This is written here what is given in the figure. You take with 1 mole of CO at 1 atmosphere here. If you have, shall I turn the lens? This one, should I
No, this is fine, sir. I can
you can manage though. So anyway, so this is actually one. So what I said, this is the problem is actually given in this figure. So you have taken initial state 1 mole of CO at 1 atmosphere and 1000 Kelvin. Now it dissociates. This is of course a constant temperature, constant pressure process, as I have written here. And then in the final state, it is not marked that it is not giving us equilibrium state. This said final state, and we'll find out whether it is equilibrium state. That is the question actually. So final state is what? It has dissociated partly and it produces 50% CO and 50% CO2 mixture, and carbon solid has been deposited through the reaction. The reaction you can clearly see 2 CO goes to CO2 plus carbon. Very simple reaction and very popular reaction. And this is the final state, temperature, pressure remaining the same. So this is in nutshell the problem. The questions are actually important. 3 questions have been asked. First, is the system at equilibrium in the final state, whether it is an equilibrium state. This is the question. Second question we will take up the heat interaction. So this is. So you see this actual relevant reaction as I have written. This 2 CO goes to CO2 plus carbon solid, and these are the delta G0s data given in the problem. So actually this is the data I have used. As you know, delta G0 CO2 minus 2 delta G0 CO. That is actually as it should be for the reaction. And these are the data. When you substitute it, you got this. And this we call this equation 1. I will actually refer to this equation later. So equation 1, this is delta G0 as a function of temperature. Now the temperature being 1000 Kelvin, get delta G0 and get equilibrium constant as usual from delta G0 is minus RT K. This is the beginning point, and you have a comment on the problem by finding the equilibrium constant. Then let us see what is Q is what? Actual state is equilibrium or not. So find out in the actual state Q is what. Then Q, okay, let us see Q is what. This we started writing last class, and so we will start from last class. Q is what? Actual ratios. What is this? You know, it is actually the expression for equilibrium constant, but actual. So PCO2 by PCO square. You know, but only actual. Actual, not okay. I repeat, how will you write Q ever? Write K. K is what? This times activity of carbon, which is 1. So what remains? PCO2 by PCO equilibrium. You just write at actual. That is the Q. What is this value? Please. Sorry. So PCO2 is what? Can I write this? X CO2 partial pressure is, as you know, mole fraction times total pressure. X CO square times 1 by P. P is the total pressure. P is, I am not actually writing. You know the answers of the actual. What is this value? 1 atmosphere. So simplify it. Okay. Actually, I am actually disturbing. Okay. What is XCO2? What is given? 50% means mole percent. When it is written mole percent, you consider say mole percent. You mentioned volume percent. Okay, you just try to convert into mole percent or apply. So mole percent. So mole fraction is what? 0.5. Actual state. At this state Q, we are discussing whether this is equilibrium state or not. Find Q and find K. K is already Q. U is what? XO2 actual is what? 0.5 over 0.5 square. This gives you 2. Yeah. So what is your observation? Tell me. Q, which is equals to 2, is not equal to K, which is equals to 0.636. Q is not K. That means the final state is not an equilibrium state. Either Q less than K, this is actually no. So at equilibrium Q is K. So the final means state 2. I have given final state or state 2. So the final state is not an equilibrium state. So the final state is not the equilibrium state. Equilibrium state. You write this. This is answer to part A. Answer to part A. Answer A. Answer A. B. Now take up B here. Start. Oh, this is both sides. Don't you? B. Second part. Okay, what is this? Calculate the heat absorbed or withdrawn from the system during the process. As this goes, this thermostat at temperature, the thermostat is the surrounding. System will reject into the surrounding or will take up from surroundings. Okay, this. So we have to find the heat, means Q. So that is, since it's a constant pressure process, so it will be equal to delta H. You try to find out this. So this is actually so to find, next is find the moles. I'll get you to this answer, but this is a preparatory. To find the moles of CO dissociated to arrive at state 2. This is actually the, what is this called? This is actually what is called. Just we try to find how many dissociated. I'm writing as usual. Certain has dissociated. See, dissociated and producing CO2. So what is the extent, etc. How many moles rather? So you please write 2 CO goes to CO2 gas plus carbon solid. I am always writing this way. Just writing. This is my habit. Okay. Identify the phases. Okay. So what is this? So initially moles. Initially what? Initially. Right. Initially. How many? Right. Usually CO how many? You know very well. 1 mole taking. 1. Okay. And how many there? None. This is, and moles state 2. And moles, moles again state. Initially means state 1. Right. Initially means state 1. State 2. Okay. State 2 is how many? You consider 1 minus x mole. X mole has dissociated. If it is x, then it will be what? X by 2. X by 2. You check this, please. Moles, moles state 2. Initially means state 1. So right here, state 1. Initially means state 1. So this, what is your criterion? 50%, 50%. So as given, XCO2 is XCO rather, XCO is XCO2. The final state. At state 2. At state 2. 50%, 50%. State 2. So what is this? That is 1 minus x is x by 2. Or what you get? 3 by 2x, or x is 2/3. Please check yourself. Simple calculation. X is 2/3. 2/3 mole has dissociated. This is clear. 2/3 moles of CO has dissociated. That is 2/3 mole of CO. 2/3 mole CO dissociated to arrive at dissociated to move the system. This is it. Yeah, leaving the movement of, right, as the system moves from, as the system moves from system moves from state 1 to state 1 to state 2. No problem. Now, what is the question is what? How much heat reaction, how much is heat interacted, absorbed or withdrawn from the system. Remember, that is a thermostat. Otherwise, isothermal process means thermostated. So what is this? Now let us see, if 1 mole, tell me, if 1 mole completely dissociate, okay, see what is this? This delta G0 is what? This plus this. What is what does it mean? Delta H0 is from 1, tell me, from equation 1. That's why I'll save this for the entire discussion. Okay, from 1, what is this? Delta H0 is what? Minus 170,700. Will you accept this? Because remember, when two terms means very easy. This is delta H0 minus T delta H0. Two term delta G0. Three term is actually no. Three term serious. Easy delta H0. Don't ever, okay. Delta H0 this now. So now under constant pressure, heat is required, not enthalpy change. Now under constant pressure, you know very well, under constant pressure, Q is nothing but delta H0. So how much this heat? So what does it mean? This is the heat interaction. Heat will be rejected if this is correspond to what? What value? For this you have written means this value you should always refer to number of moles. Okay. Sometimes it is implied. If it is implied, how this is the delta G0 for how many moles of CO? Sir, 2. Or 2 moles of CO dissociated, reacted, or 1 mole of CO2 formed, or 1 mole carbon formed, in whichever form. One you write, others are automatically, okay, understood. So this is so when 2 mole dissociated, how much heat is liberated? 1, good. So when how many has dissociated? 2/3 mole. So delta Q is for 2 mole this. So this will be, shall I write? Okay, minus I shouldn't write. I will say right. How much it is that you write? Okay, minus right. Minus 170,700 divided by 2. Make it 1 mole. Then how many moles you are dealing with? How many moles dissociated CO? 2/3. So this will be minus 2 to cancel. Minus 56900 joule. So what will you comment? This much is negative means release, because this is release actually, no. So actually this is exothermic reaction, and this see, and the opposite is endothermic. This CO2 plus C goes to 2CO. So this is the, so what is the, how to write? So that is 5690 joule of heat. What is the question is will be withdrawn from the system. Will be withdrawn means will be rejected. System will reject. Negative will be rejected by, will be given to the surrounding. Will be withdrawn. I am using his language. Will be withdrawn or rejected. Withdrawn from the system, and of course you mark that this is the answer to the question, the part B. Over. Next is C, part C. Again, I am trying to find this. This actually is the process thermodynamically possible. So what I will do for this? Okay, this I try to find this. Let us see how many moles actually have. So let us see. This is actually required some discussion. Thermodynamic again to find the moles of CO, again I am finding CO, moles of CO dissociated to arrive at equilibrium state. At equilibrium state, not state 2. State 2 is not an equilibrium state. Yeah, at state 2, at equilibrium, at the equilibrium state, at the equilibrium state. At the equilibrium state. So you can repeat this. So repeat previous. So write once more. 2 CO gas goes to CO2 gas plus carbon solid. Initially, right? Initially, I am not writing moles. You understand? Actually, right. Initially, moles very important. Moles. What are the values? Tell me. 1, 0, and at equilibrium, right? At equilibrium. Now you are considering equilibrium, not set 2. See, if it were equilibrium. So what it will be again? Consider 1 minus x. I am not changing this 1 minus x. It will be obviously x by 2. X by 2. Solid though does not matter. So what is the in total gas? This you do in total. Last day I forgot to mention, in total when I do solid excluded, meaningless. In total you using the partial pressure, mole fraction time total pressure. These are all ideal gas laws. Okay, things. Okay, so it applies to gases only. So total gas, in total empty gas. How much it is? 1 minus x plus x by 2. Solid excluded, so it is 1 minus, right? 1 minus x by 2. So I am absolutely, this is in total. It will be used. Why? Right, equilibrium constant. Next is, now I will ask you, is 1 minus x equal to x by 2 as last time? As last time, that was a state given, hypothetical state. Consider a hypothetical process, hypothetical state 2. See, it is journey, initial state to journey commences and ends at equilibrium, but if you actually extend it, that will be impossible. Let us see. Let us not disclose everything. So what is this? In total. So K. So what is that value K? I have saved this for you. 0.636. So start with this point is what K. You write. I have no. Yes, I have given. I cannot. I have developed good habit that temperature always attached. Equilibrium constant temperature. Very nice habit. This is what you know very well. Tell me. PCO2 activity of carbon, as you write, always write, and it is the simplest of a reaction. And at equilibrium, you write, if you are interested, write at least once on that it is equilibrium state reference. Equilibrium activity of carbon is what? Please write 1. So PCO2 by PCO you write in terms of NCO. PI apply PI is so I am writing here PI is for you. You know very well, even though PI is Xi time. Good boy. Xi is what? Ni by N total means Xi covered. Xi covered times total pressure is P. I am writing. P total. So if you recall this, if you apply this, I know very well, you can very easily find out. You follow this way: NCO2 by NCO square. NCO square. Actually, I will go. And this is the last line maybe here, XO square, and equilibrium. You should understand this is equilibrium. Okay. Times what branches out in this? Ni by this Ni is over NT. NT is what? By total pressure. Total pressure will be 1 by, you check this NT by total pressure. If you have any doubt, you can pause for a moment and check this. Is it Ni by N total? Okay, each case. PCO2 is what? NCO2 I am giving you. PCO2 is what? NCO2 by N total times P. PCO is what? NCO by N total times P. So you see, this is follows this. N total actually, I have made a mistake. Certainly I have made a mistake. Okay, P will be upstairs. No? N total. Okay, let me check. PI. This is correct. This is correct. Pressure. You go by the pressure. N total will take the other position of the fraction. That if it is lower, that will go upper and upper. If it is P is Z for you. What is the P here? It's a time pressure, pressure by pressure square, total pressure. So P will come in the denominator. The into the obviously this is so easy. Obviously it will go to the numerator. So numerator that branches out. Now substituting nothing else. Keep it here. These are the this pertain to equilibrium value. So can I? This part is actually I will not come back to this. I will come back to the answer maybe. And this actually x is 2/3. I'll actually recall this. Maybe I just it is better. I don't have much option. Sorry. Very sorry. I don't actually. Achha, I'm just removing this. This actually. Continue from give a star here. Continue here. And just don't disturb this. 2CO gas is CO2 gas plus carbon solid. You just start this start from this point and yeah. You just for some reason I'm actually saving this one. I want to save this. So I am not removing this because this is what LCO to apply this. So you just keep on doing 0.636 is what is this value LCO2 value. LCO2 value. This part into equilibrium. So this is equilibrium. Both all are equilibrium. What is equilibrium value? Go x by 2. Okay, x by 2. Right. This is equilibrium. These are not equilibrium. This is the hypothetical state. It was I consider x by 2. What is the NCO? NCO is what? 1 minus x. 1 minus x squared. 1 minus x squared. Then what else? In total. In total. What you call me? 1 minus x. This is given to you. 1 minus x. Very good. And what is the p? P is what? 1. This is p is the right one. Okay. P is 1. So what it is actually? So I write here x times 2 minus x. Okay, now class 8, 9, what you call it by 4 times 1 minus x squared. Happy? This is very good. This x squared. So what is the value of x? Turns out to be this quadratic equation, and if you do yourself, and you will find this. Let me check this x into 2. It's actually I know the answer. So, but I will check actually it's looking very nice. Or x is 0. This is actually equilibrium though. 0. I tell you what. This 2/3 actually. X is 2/3. 2/3 means no, 2/3 is the previous one. This time x is will be what? Calculation quadratic will give you x is 0.47. Just shall I write another line or if you simplify this since I have the result calculation here x square. You simplify, if you do yourself, you can compare this. X square minus 2x plus 0.72 is 0. Quadratic. This is quadratic equation. And x is, this leads to x is 0.47. This leads to x is 0.47. Okay. Acha. So, okay, good. So, what is your comment? So, that is when follow what is x 0.47. So that is when 0.47 moles CO have dissociated starting from 1 mole have dissociated and forming in bracket you write forming. Tell me forming you complete this forming dissociated forming what? 0.235. Very good. X by 2 0.235 who mole of CO2 and exactly that also complete this 0.23 mole of carbon solid. Additional statement. So when 0.47 moles will be dissociated, the equilibrium will be struck. Equilibrium will be attained and no more movement is allowed. System can equilibrium is the goal. Delta G is 0. All spontaneity is exhausted. Means no more fuel, you may call it, no more oil, no more motive force, all dead. So when it's done, equilibrium state is reached. Equilibrium, equilibrium is when equilibrium state I am writing. state is attained, and no more attained, and no more reaction, no more dissociation, no more dissociation of CO, no more reaction writing, no more reaction, no more dissociation writing, dissociation, more dissociation of CO is possible. Please. So can I remove this? Okay, this part is over. So remove this. Huh? Good. No. So what is your question? Answer to the question part C. I've written part C. I have not written. No? Yes. I have written. No? At the below. No? I wrote. So what is the answer? Hence, your conclusion, comment. Hence, what is the process thermodynamically possible? It says what is, it will stop, but it says how much? 2/3. 2/3 mole means 0.6 mole will dissociate it. No, it will go on. So what is this? Madness. Total unthermodynamic process, hypothetical process. So hence it is not possible. So is the process. Hence it cannot overshoot. Starting from the initial slide, I give a sketch once more. That's favorite, your actual popular sketch, favorite sketch. I will give this, but let me write this answer. Hence, then you will understand more if I give you the sketch. Okay. Hence, the process is thermodynamically not possible. Right? Answer C, and problem is over in a sense. But I will continue some discussion. I will continue. No, D. I'm just writing here. D. Not asked in the problem. Not asked in the problem. Although not asked in the problem. Although not. Oh, by the one thing I missed last class. Please give the reference here, or very venerable person, Doctor RJ reference. R. Schumann Jr. Reference R. The spelling is very tricky. See, every time I consult this reference is RCA. This is actually this spelling is what RCHUH SCHUH MANN RCHUH MANN. A junior should be the actually identifying. Yes, okay. So I acknowledge this problem. This is not asked in this problem, but although not asked in the problem, we are interested. We are interested to find delta G prime Tp between 1 to 2. 1 to 2 means as given in the problem, as to find that as discussed in the what is part 1 is a systematic view. Okay. Shall I give a name to this? As shown in figure 1. That will then I have to figure 1 as given in figure 1. Original problem as given in figure 1. Then I will actually ask you something. Delta G Tp. I should at least 2/3. You will remember this 2/3 mole. Okay. I think I can remove this because this problem is all discussed. Problem is over, solved. Additional discussion. Everything is with me. I will show you one thing. First of all, right here. See, I'm plotting. Oh, what is delta G prime TP? So what I'm plotting here? G prime TP I'm plotting. Recall this class, minimization, etc. class. Refer. TP, this is what? And against, say here, this side and this side. Let me draw this. This is the equilibrium, minimum, right? Equilibrium state, minimum. Okay, G prime TP plotted against, what is this? Mole CO. Mole CO I am writing. What is the starting value? 1. And you want to the other extreme. When it is 1 mole to what you will get other extreme? Half CO, other extreme, sorry, 1 mole, the other side is half CO2 plus half carbon. 1 mole full, half CO2, half carbon. 1 mole CO, mole CO, sorry, 1. Achha, 1 mole, right, 1 mole CO, right, 1 CO. So mole CO is, mole CO in this decreasing, remember, decreasing. How it is? 1 here, decreasing. How you show this? 1 this side and 0 other side, decreasing. And who is increasing? Obviously, guess, mole CO2 increasing. This, you understand this? This is the extent of the reaction. Extent of the reaction. Here nothing, this is initial state, okay? Equilibrium state. What is given? What is this? At the equilibrium state, what is the CO content? Please follow. Equilibrium state, you all with you. 0.47 has dissociated. See, 1 down, 0. So equilibrium struck. What is? How much has dissociated? 0.47. That means how much is here at equilibrium? Tell me. 1 0 I have given to. So equilibrium down. 0.53. 0.7 dissociated. What remains at equilibrium? How many moles of CO dissociated? 0.47. How many is remaining? 0.53 moles. Right? All you write 47% dissociated. You can whatever you like. From 1.47 used up and equilibrium stop. So equilibrium concentration are what? What is remaining at equilibrium? That is the equilibrium activity or shear pressure. That's always what at the equilibrium what remains. So it is actually so 0.5 yes, or increasing. So 0.53. And what is the state? Can you now tell me what state? The state 2. This is the equilibrium state. Equilibrium state. Right? I'm writing once more for you. Oh, not CO2 increasing. This CO2 increasing unnecessary. Mole CO. If you follow this, what is this? At equilibrium. This equilibrium already marked. It will be redundant, unnecessary. Right? I have shown this. I am equilibrium. Arrow maybe. Equilibrium, come down. What is the state 2? Where? I'll place where? How much has dissociated? It I have not have saved. 2/3. 0.6 has dissociated. That means what is the value of CO remaining? 0.33. Maybe this is the right here state 2 given in the hypothetical process. What is the CO content? CO content here, tell me. 2/3 dissociation means point, even less, this was decreasing, even less. What is this? 0.33. 0.33 mole CO. 0.33 mole CO. So you have all the sketch for CO. Consider CO. So 1 down. So reaction starts means 1 down. Okay, down to 0.53 all over. Reaction stops totally. Then, but since hypothetical process, but we can always mark this. This is the value because we are the whole span is this 1 mole CO2, 0 mole CO, or 0 mole CO2 this side, 0 mole carbon this side, to half mole CO2, half mole carbon the other side, other extreme. So this is the problem. So now you clearly see that right nicely. Half C. Don't touch this part. It's okay though. So you see now I have understood why this process is impossible. Question whether this to this possible. This to this. This state 1. Why is this happening today? Because so right here state 1. Initial right here. This is state 1. Figure. Refer to the figure 1. State 1. This is the state 2 in figure 1. State 1, state, not equilibrium. What is right? This is equilibrium. There is a mark here, equilibrium. Over to, it's okay. Mark here. So NCO2 increasing, additional statements are given bracket. So follow CO. Okay. So you see, start from here. Is it possible? Question is asking. See, I am giving the sketch now because I have calculated. We have calculated. So when it is said here to here, how will you decide whether it is possible? So you have to check whether it has overshot the equilibrium state, got past the equilibrium state. Since this state 2 has got past the equilibrium state, has succeeded the equilibrium state, so it is an impossible attainment. Difficult. No, it is not possible. It will stop there. So this is the reason this process is. See, this is your 2. This is the equilibrium state. Okay. Now question is not part of the problem. We are delta G prime TP. First, you say, tell me what is the delta G prime TP. See, I actually spent some time in the class to distinguish between delta G prime TP and delta G without any subscript. Pure delta G. That refers to what? At a given state. At any state delta G means product. How delta can you come? This I asked. How a delta may be relevant when we are talking of a given state, one state. Delta we actually used to consider 2 state, initial, final. At a given state, delta is what? Is G of, at the same state, G of product minus G of reactant. And what is this? And what is this? What is delta G prime TP? Now, sir, 1 to 2. System is moving from 1 to 2, whatever. So 1 to 2. 1 to, so delta G prime TP is the relevant term. Delta G prime TP from 1 to 2 can serve as a criterion. This also I discussed. Delta G always for a given state whether reaction will occur or not. This is actually universal. No one can stop. Universal. And this everyone is using. No one entropy universal. They don't consider for spontaneity. So delta G. So this is the problem. So delta G prime TP. So what? So but this is this. But yes, is there any limitations on this? This I discussed in the class. Limitations. What I said. This you will see. This you will see now. Okay. Let me calculate this. Okay. We see clearly it is negative. 1 to 2 means 2 minus 1. 1 to 2 minus 1. This energy. This energy. This is, remember, energy increasing. Negative. So delta G prime TP is turning out to be negative, and think in the meantime, so negative still it is impossible. First of all, you decidedly find out delta G prime TP. Don't count on this figure, which is actually qualitative figure. Quantitatively find what is the delta G prime TP to find delta G prime TP. So this is the next. Shall I? This part is actually not. This whole thing is not required anymore. So delta G prime TP. You please tell me. I'm fine. Delta G prime TP. Acha. Start this. Shall I write here? It is better. I can write here. Acha. Delta G prime TP. Let's continue here. At least as much you can. 1 to 2 is what? Nothing but G prime TP state 2 minus G prime TP at state 1. State 1. For this, you must write state 1, state 2 very nicely. Okay. I'm still refer to this. Equilibrium is over. Let's say all discussed. Go back to this further analyzing and dissecting this problem, this hypothetical process. So, sir, many people will be fooled by saying that are negative, but still impossible. I will show you. Figures show negative. We will quantitatively find negative, and still we will stick to the answer that it is impossible. Then we have some doubts about the application of delta G prime TP, which I have already covered. But today is the practical application, and very nice with this nice problem. So this is state 1. So for this state 2, state 1, state 2, right? State 2, best state 2. If you ask me what is the state 2, write this. I am writing. It is better I write. I take this. Go top. Go to the top. Here, rise. You draw a line here. Don't disturb this. What is the G prime state 1 to state 2? Very interesting way you write. So this may be a new experience for you. I am writing state 1, state 2. See. So I am writing 1 mole CO. As I see, CO. What temperature pressure? Please tell me. 1000 Kelvin, sir. and 1 atmosphere. This is my state 1. Underline. This is my state 1. 2, 1 to 2. State 2 is what? Tell me accordingly. Tell me 1 mole CO. Please tell me what is this? No, state 2 is what? Oh, 2/3 I have already said. What is there? Oh, you got the answer. Point you wrote somewhere. Huh? You tell me what is this? 1 mole 2/3. 2/3 dissociation means 1/3 remaining. Na? X is 2/3. So 2/3 means 2/3 mole of CO has dissociated. So 1/3 remaining. Na? Right. 1/3 mole CO. 1000 Kelvin. I'm giving you, and plus what else? Plus 1/3 mole. CO2 will be 1/3. 2/3. If 2/3 dissociated from this, 2/3 dissociated, it will be 1/3 CO. At temperature and pressure I'm giving, don't mind. 1/3 mole CO2, that is also 1000 Kelvin. Oh, happy to? It's okay to? And then pressure I'm giving. Then what else? 1/3 mole carbon solid, right? 1000 Kelvin. What the pressure is exerted in the state 2? Figure and right. Figure and right. 1 atmosphere total. The solid is subjected to 1 atmosphere, and they together is 1 atmosphere. So that means what is the share? 50-50. 50-50. Is it 1/3 mole? 1/3 mole is sharing the gas also. Pressure is exerted on solids in this 1 atmosphere exerted on us, on this everyone. Okay. And gas if is they'll share. So what is the share here? 50% share means what pressure? 1 is share. You actually all said. So this is very nice way, funny way of writing an reaction. This in state, what you write? Right here? Tell me. Right? This right state 2. Right here. State 1. As seen in the figure, I have written. Now get delta G, very nice way. So I'm just removing all these things. These are all removed. Not required anymore. Not required. Just I will try to find out delta G negative quantitatively, that value quickly. So delta G, finding out delta G. So delta G prime, this is a constant temperature process. Clearly see delta G prime Tp is what? This is a G prime Tp. Acha. Delta G. Acha. Don't do delta G is what? Right. G prime Tp. Once more I have written here. I have written here though. Acha. I am writing delta G prime. I will not repeat this. It takes time. So delta G prime Tp is what? Tell me. I'm writing. Acha. Break up. I'll get the delta G. To find is how much. You give a question marks here. Is how much. This is the question actually. Additional question we have invited ourselves upon ourselves. Okay. So what is this? 1, 2. State 1 to state 2. I'm giving break up. Easy break up for you. Breaking up in 3 steps. Break up. 3 steps. I'm writing. You follow me. 1/3 mole. 1 is broken into 1/3 and 2/3. 1/3 mole CO 1000 K 1 atmosphere. Happy? This is 1/3 mole is going into what? 1/3 mole. Take a look. Left hand side, right hand side should be maintained. So then that is the breakup. 1/3 CO, 1/3 mole CO. How much? 1000 Kelvin. Right, as you see, 0.5 atmosphere. You have to answer this. I am giving the breakup. Step A maybe. Step B, what remains? Is 1 mole CO 1000 K. So 1/3 I have taken for this 1/3 balance. So 2/3 still are due. So 2/3 mole. Tell me mole CO. Remember so many breakup you have enthalpy calculations. Okay. 2/3 mole CO. What you write? Same result. Same right. 1 atmosphere. Right, and then what it is goes to right. I'm writing. Follow 1/3 mole. I'm writing 1/3 mole CO2, right? 1000 Kelvin. And what I'm writing? 1 atmosphere. I'm writing 1 atmosphere. It is though it is 0.5 atmosphere, but then I will make amendments. Okay, manage this. Okay, here for what reason you can guess. Plus This I covered. This right hand side, this I covered. 1/3 mole carbon, solid, 1000 K, 1 atmosphere. You can easily recognize this. What is my plan? Okay. C, complete this. What remains? This gentleman was not 1 atmosphere, 0.5. So make that step. Okay. So this should be 1/3 mole CO2, 1000 Kelvin, 1 atmosphere goes to what? Tell me. 1/3 mole CO2, 1000 K, what? 0.5 atmosphere. That's it. Very good. Acha. So remove this unnecessary. Find one by one. Delta GA. Right. Now delta G, delta GA, delta GB, delta GC will be the delta G prime. Okay, a combination of this. Delta GA, how much? Tell me. Are you convinced though? State one delta G prime. Then see, you can check. Easy. Delta GA, can anyone? I'll be very happy. C. Leader will tell us. 1/3 mole CO. Okay, did very well in the examination. 1/3 mole. Did you have this problem? No, you didn't have this problem. No, chemical reaction problem. No. This type. Assignment 7. 1/3 mole CO, 1000 K, 1 atmosphere goes to 1/3 mole CO, 1000 K, 0.5 atmosphere. Tell me, what is the free energy change? Forget everything else. Focus here. 1/3 mole. You are using n moles. 1 mole. 1/3 mole. No problem, sir. CO, ideal gas you have considered. That gas is CO, happens to be. 1000 K, what does it indicate? It is taken. What it tells me, if I any question, if I ask, that is a prompt actually. That will be a prompt. I don't want to. So you tell me what do you mean by this? What is this? Are you familiar with this? The first line. Have you ever come across this process? First step in the form of any process. Suppose ideal gas is a system. Which process it is indicating? Which process? Isothermal process. Say famous. I should not draw this. If you ask me, how many times that come back? If you understand the initial classes, that famous P1, V1T. Should I write this? But it will be so much retrogression. P2, B2T, ideal gas. This is the question. And this side is actually, what is this? P versus P. PV diagram. Let it be. Now answer. Open. These are the isothermal process and much discussed, like adiabatic, much discussed. Constant pressure, constant volume also discussed, and tabulations. Reversible. So please tell me what you have found for this process, isothermal process. What you have actually known for this process, or what you have gathered, what you have collected, what are the different thermodynamic properties perhaps for this process you have found different thermodynamic quantities for this process. You have already done in your syllabus. What? I listed. Can you tell me? Q, very good. W, very good. Then delta U first cover. First go to the first law. Three down. See, one actually could not answer. 3 down. Q, W, delta U. I will ask you also this value. Just division to show you, to give you some courage that we are same old thing. Only number of such things are added together to make up this. So what else? Delta H you said. Delta U means delta H will come soon. And then what else? Delta S, next entropy. G is actually derived from entropy. Delta S, then delta G. Still another, if you are interested, another, which delta A. Delta A is the Helmholtz free energy. G is the gives you. Seven items about this, you know. One by quickly, very flurry, quickly. Q is what? For this person, 1 to 2. Q is W, very good. And W is what? N moles, Ln V2 by V1. Means W down, 2 down, delta U, you see, you will tell us. Delta U, very easy question, that's why I asked you. Delta U, so easy that you will be embarrassed. Easier stop. Zero. It is zero because isothermal process. NCBDT you apply, said for ideal gas always NCBDT. If you forgotten, DT is zero. Or for ideal gas, internal energy is function of temperature alone. For ideal gas, and temperature is fixed. So where can be changed? Delta is zero. Delta H is zero. 5 down. 4 down. 4 down. Delta S and delta G is actually is not zero. First of all, they are unlike delta V, delta. What is the delta S? Anyone? Again, isothermal. That is actually final shape is RLN V2 by V1. It is actually generally CBLN T2 by T1 with N moles, NCBLN. NRLN V2 by V1. Since isothermal part gone, V2 by V1, that can be P1 by P2 also. Delta G, yes, so called delta G, delta S is NRLN V2 I have given you. Delta G, or what is the source equation? Then that will be also.
H minus
that is too much original. DG is what? VDP minus SDT. So effect of pressure and temperature. So the pressure is effect pressure and temperature. So temperature effect is what? VDP minus SDT. That term will exist. VDP. Integration of VDP is actually nRT by P, nRT ln P2 by P1. All over. Okay. So please. So here also pressure effect. Isothermal nRT ln P2 by P1. Delta G. So nRT, N is how many? 1/3? Yeah, 1/3 or I'm writing RT, nRT, RT, ln, as VDP to easy. DG is VDP minus SDT. Oh, VDP. nRT ln P2 by P1. P2 is what? From this 0.5. Good boy. 5 by 1. Is it right? This 1/3 ln 0.5. Right? Once more. R is how much? Tell me. Achha. I'll write at the end. I'll substitute the value. R is how much? You know, 8.314. T is what? Numerical, quantitative. Delta GB. This is actually you have to some inner look. Delta GB. Can you recognize what it is? I'm very happy. What type of it is? See, I told you in the breakup you see some are actually. Okay. See, what is this? You see, 1000 Kelvin, 1 nanosphere, 1 nanosphere. Standard state. 1 by 3 delta G of formation of CO2. Very good. You are very smart, I see. You're very good. 2/3 mole, na? What's it? 1/3 mole, you said. How for 1 mole? Right here. See here. Delta. See here. For tell me, I'm writing. Delta G0. 1 can I write? Delta 0 1 I can write. Tell me, delta G01 means standard state change. Standard change delta G01, but this is for how many moles? 2 moles CO2. How many related to 2 mole? So it will be related to 2/3 mole. So by 2. Actually, by 2 into 2/3 already done for us somewhere. By 2 I have removed this. By 2 initially, divided by 2. And delta H0 was done. Next. Delta G0, this is okay, don't worry. Delta 1 by 2 into 2/3. What is this value? I'm writing. Achha. This I'm completing. Delta G1 is what? Tell me. This much. Delta G0 for how many moles of CO? 2 moles. Is it? 2 moles were considered. This you have to. Extensive intensity. Go back. Extensive intensity just every moment you are required. For 2 moles. This is, if we not written, implied for 2 moles, 1 mole, etc. It's okay. So for 2 mole, for formation there is no difficulty. Formation is 1 mole of the form. So per mole, everyone knows in formation. But this is not formation reaction. So per 2 mole. So but we are interested how many moles are actually for delta G0. For this actually delta G01 I have written. So good boy. So what it should write delta G0 for this. Let us calculate this 36. Let me tell me. Delta G01 is how much at that temperature by 2 into 2/3. Have I made a mistake? Perhaps let me check. Delta GB. I have made a mistake. You check this. What mistake I made? Delta quickly. This is important though. Delta GB is what? Oh, what I have learned here? I am wrong, no? He's okay. One third, correct. It's correct. How much it is? 376, 376 is let us see. Yes, correct. 100% correct. You give the right. Give the figure. 12. Will you buy this? This part is okay. But tell me.
Sir, we know that del G is equal to VDP. So how and
yeah. This line you are talking about. This line.
that is what
This is a chemical reaction. This is actually isothermal process. Gas is moving for isothermal process. Okay, of a gas.
but that is PdV for isothermal reaction.
Uh-huh.
How is it equal to VDP?
This is actually your initial questions. Okay, dg is vdp. Delta. Sorry, acha. This is better. I explain this. This will clarify you. Suppose you are in doubt. Delta G is RTLN P2 by P1. Right? It's okay. NRTLN P2 by P1. Delta G is, NRTLN is one I am considering. Delta G is RTLN P2 by P1 or NRT cells, you may doubt. NRTLN P2 by P1. This I am trying to establish quickly. From your delta S, have you got any doubt? Delta S, RLN P2 by P1 you told me. RLN P2 by P1, NRLN P2 by P1, that you don't remember? For isothermal process, for this process only. The question is okay, I have followed your question.
No, we know that delta G is equal to VDP, right? For
DG is VDP, okay. DG is VDP.
but NRT on P1 by
P2 by P1. VDP integration 1 to 2. 1 to 2. VDP. What is VDP? B is NRT by P. B is what? B is what? The NRT dP by P is what? Quick. DG is VDP. Now, is happy though? You doubt? Now, do you have doubt here? DG is VDP minus SDT though. Achha, minus SDT I am writing. Then cancelling. VDP. Delta G will be what? 1 to 2. 1 to 2. 1 to 2. What is B? What is B? P by P. What is this? N is out, R is out. NRTLN P2 by P is okay though. Achha, see how many, see, it is so consistent subject and okay, that suppose you have forgotten, but delta S you are very strong. Apply that. Delta, right here. Let me, since you have asked me, delta NRTLN P2 by P1. So this is also subs here. Okay, but I'm alternative. I'll also show you here this alternative. Delta G is what? Delta G is H minus TS. First line is first line. G is, we don't know beyond this, sir. Sorry, sir. But we know, this we know from very confidently, G is H minus TS by definition, sir. Very definition. So delta G is what? Delta G will be what? You know, so where I am. So since alternative. Delta G is what? Tell me here. G is H. Delta G is delta H minus delta TS. Since T is a constant, T delta S. T delta S. What is delta S? RLN V2 by V1 means minus R by NR. NRTLN V2 by V1, opposite of this NRTLN V2 by V1 is actually, it will be P2. Tell me. Achha, I am coming to this. Achha, delta H is what? By the what is the delta H value? 0. So only this is. And what is this? Minus T NRT. LN, tell me, what is delta H you said? V2 by V1. V2 by V1 is by itself is sorry. V2 by V1. V2 by V1 itself is P1 by P2. But there is a minus back P2 by P1 and same. V2 by V1 is P2 by P1 isothermal. Again, why sir? PV is constantly isothermal. Apply the properties of isothermal. This is all about isothermal process. Okay. Happy though? So many. Okay. So this is correct. What is delta? This is Sukolan will tell us. Sukolan knows everything actually. Let us see. See the C step C. Step C. Just you answer very quickly. What is this? Then I will be very happy. Yeah, you don't have to say anything. But seeing this, sir, this is this. This will be that. That's the same as A. Yes. What's the name? What is there in name, sir? So argon. Ideal gas we consider. Oxygen, CO and CO2. Same happens. The same result. So 1/3 is okay though. Everyone? 1/3. This is your answer. So what is the delta G prime TP 1 to 2? So we are waiting for this delta G prime Tp 1 to 2, right? Right, I am breaking up here also. Okay, this I don't have to. I already shown. This is this. Okay, this is what state 1 to state 2. Sum total of this. What is this? 1/3 twice 2/3 or TLN 1.5. Write this quickly. Plus second is first third covered, and this is 1253.3 joule. What is this? 2/3 TLN 0.5 into what is R? 8.314. What is the T? 1000 Kelvin. So you do this yourself, and you will be satisfied to get a value of. So I should not waste time. So this is the whole trouble, that minus 2589 joule. You do yourself. Check yourself. Joule. Answer. What is the delta? What was the question? Part of the question that I actually inflicted upon ourselves. That is delta G prime. Answer. 1 to 2. Answer. Answer. Now question is what? Again, see, as you expected, negative. Not only just negative, sir, minus 2589 joule. It is not 2590 joule. 2589 precise, sir. So negative. Then the question comes. But so how? Now remove this. Remove this. So how is it possible? So question. So mysterious. So that's so. Got you right. So how is it possible? How is it possible that the process is impossible? I said. What is the process? It's not possible. This to this impossible. The process is impossible, even though process twice have. How is it? How is it true? How is it true that the process is impossible even though delta G prime Tp is negative? Your answer will be that delta G prime Tp is not the conclusive answer, sir. Is negative means if your second state 2 happens beyond equilibrium state, it will not work. I said sometimes it works, sometimes. How long? When it works? When delta G prime Tp. So note this. So all over. So remove this. Note this. Note this. All remove. All problem. Only 2 lines you comment, which you know though. So the comments. Delta G prime comments. Note. I am writing note. Delta G being negative is negative. Is negative. Is negative is an universal criterion. Applies to, first of all, is an universal criterion. No subscript. No subscript, no nothing, no constant, any process on earth is negative, is an universal criterion and applies to, tell me, this is very important, applies to a given state. A given state, no 2 states, 1 state, to a given state to find whether the reaction under consideration, the reaction is at that state is possible, at that state is possible, is at that state is possible, and writing on also note is possible. Okay, is possible. That is again. Note further here, delta G is here, delta G, just delta G means oh, Baba, 1 state. At this state, I have taken something ammonia, etc., permanganate, hydrogen peroxide, etc. Whether reaction will occur, I have added a state, apply. Any constant, don't do adiabatic, isothermal, constant pressure, constant volume, all okay, juggling you do. Delta at a state. So then what is at a state? Why is the delta? At a state delta? Note further that delta G is at a state is G of product minus products minus G of reactants. At, right, so all remove this. Reactants at that state. At that state. Again emphasize. So again, so it is emphasized that this delta G, this delta G does not consider two states. I will not write anymore. This is clear. Does not consider two states. One state at a given state. Does not consider two states. It is about any given state. It is about one state. Does not consider two states. Two different states. Does not consider two states. Initial state, final state. It is about one state. It is about giving state, one state, but product minus. Then how you get delta, sir? Delta is change. Product minus reactant. So what is the product, sir? I have given this, the product actually, see the reaction you want to put. That can be done. Okay. Next is, then you write in contrast. This is now in contrast. Delta G prime Tp. Yeah, understood. So delta G prime, why prime? Extensive, don't do it. Yeah. Delta Tp is negative, will serve as a criterion. It's a criterion of the delta Tp, where right here, where writing is where delta G prime Tp is, let me write, Tp is right here clearly, G prime Tp state 2 minus G prime Tp here, G prime Tp state 1 in brackets over. So delta is negative, will serves as a criterion of spontaneity. When I talk of spontaneity, only spontaneity I am discussing. It means you have a equilibrium is what? One is equilibrium, another is impossibility. Serves as a criterion of spontaneity. When state 2 will be somewhere between, right? Somewhere between state 1 and just say the chobi. See when it will be valid, negative. See here, suppose you consider this here to here, possible. Up to this possible, sir. Is not necessarily always useless. Here to here, that means this is the critical point. So will be somewhere between state 1 and the equilibrium state. Right here, right? So many things. No, equilibrium state included. Equilibrium state inclusive. Okay, equilibrium state inclusive. Between means before equilibrium, even up to equilibrium. Up to equilibrium, possible to come to equilibrium. Possible, sir. Why not possible? Reaction go happens, but beyond equilibrium state included. That is, state 2 may not be a state, also right, beyond, a state beyond the equilibrium state, a state that transcends the equilibrium state, a state beyond or succeed beyond the equilibrium state. I think enough I have written and enough you have understood. Beyond the equilibrium state, nicely, right? That's this over. I am very satisfied that with this, finally we have finished this problem. Additional we have considered. So this was actually so much. It will be very difficult to find this criterion. Actually, what is criterion is sort of the, see, sometimes delta G very loosely comment which delta G. Don't worry. Don't worry. So one problem next, last problem of this assignment, that is which number problem is 7. Good. Shall I this? So very good. So next problem, let us start. Problem 7 and last problem. This will not take time though, but very important for you, metallurgist, iron makers, iron and steel. Problem 2, please write this problem. Two of this problem, this I will acknowledge that scale at the end. Remind me of that. Two of the oxides, let me write this problem 7. Shall I write? Two of the oxides, write this. Two of the oxides of iron. Two of the oxides of iron are, as you know, FeO, other oxides there, two of them are FeO, which you call as austite, and Fe3O4, which you call magnetite. Okay, this is solid iron. How much time? How much time?
1 hour.
Solid iron, let me do this very actually thoroughly. Solid iron exists in equilibrium. In equilibrium with one of these oxides. With one of these oxides at, what is that gentleman called, at low temperature. At low temperatures, right? At low temperatures, and exist as in equilibrium with the other oxide, and exist in equilibrium with the other oxide, right? Nicely with the other oxide at high temperature. Okay, at the other oxide at high temperatures. High temperatures. Okay, happy. The molar, the standard free energy change. Acha, I'll give this. Don't worry. Over. Determine. Data I'll give when you solve this problem. Determine which of these two oxides is in equilibrium with iron, at room temperature. Iron at room temperature. At room temperature. Well, note this 298 Kelvin perhaps. Very interesting. At room temperature and the maximum temperature. Maximum temperature at which this oxide is equivalent with iron. At which this oxide is in equilibrium with iron. Find out and remove all this unnecessary. Better. Do this. This also works, no? Solution. Start. It will not take much time. Solution. The pertinent equilibrium. This you have to pertinent equilibrium. See, it is about the story. It is a story about iron, iron oxide, APO and AP3O4. About the who will exist with whom, who will be in equilibrium with whom. Exist means equilibrium. So I have to write a, but equilibrium is what? Or reaction. Reaction or equilibrium is what? You know very well. What is this? AP3O4. Let me write the way I have written here. It is better I write that same way. Is AP3O4? Is correct. I am right. Corrected. Plus AP is what? Tell me. 4 APO. No doubt. This is what in concept. 3 involved. Very nicely. 3 involved. Delta G0. Delta G0 is what? Tell me. Tell me. Delta G0 is what? Tell me. 4. Delta G0. Tell me. Any reaction. Formation. Any reaction formation. We don't know beyond this. Minus delta G0. AP3O4. Iron will include? Iron is okay. So now I am putting the data. So data given, I will say 4 times. Write this very nicely. 4 times. You get the data at the same time. Minus 259600 minus 259600 happy plus 62.55 T. This is about 4 parties over minus what is the AP3, right? AP3O4 delta G0 is what? Minus 1091, you know, 000, and you have 312.8 T all joules. Okay, so this is nothing but what else is this very important line coming down is what? What is this? Oh, I should have 52,600. Right, 52,600. This is most important line coming. Delta G0 is 0.52 minus 62.6. 100%. Box this. You can box this. Very important data. Right here only data given in the problem. Right. Data given in the problem. In the problem. Oh, you can see here. You forgot to remind me my right here reference. Reference DR Gaskell. DR Gaskell second edition since DR Gaskell as I write always second edition. I'm not giving second edition. Maybe other edition also, but I don't know. These are edited sometimes. Okay, they are. There sometimes. See reference. Delta G0. So this. What is the? This question is now try to solve this. This is a 1, 2, 3 lines problem. So you try to answer. I've given everything to you. First you will find out what. When they coexist, these 3 gentlemen. Question is about with iron. Which of these 2 oxides will exist at room temperature? And what is the maximum temperature? This is the question. At room temperature, 298 Kelvin. So, first of all, if they want to, all, not only this, this, with iron, if they exist, then what is your condition? What is your thermodynamic condition or your understanding? So, there are 3 coexist, possible, 2 possible, 3 possible. They exist. Means they exist at equilibrium, that's why they exist. So, 0 at equilibrium when that equilibrium 2-phase equilibrium, 3-phase equilibrium at equilibrium when the three phases in the above three phases namely name them AP, APO, AP3O4, you know, coexist at equilibrium when the three, what is your understanding? If they are at equilibrium, then what will happen? Delta G will be 0, sir. Delta G is 0. So 0 is what? Delta G. And what else you can further add in this present case? Delta G is as good as delta G0 because they are all at center state. No gas phase involved. So delta G is as good as, because of pure states, these are all pure, it's not written, right? Solid, will you write this? AP3 write here solid, just have random checking. What is this? What is this data? Is it 4 times? Forget 4 times. What is this data? What is this data? Delta? No, full. What is this? Full. This here to here. What is this data? 4 times I have written. Delta G not APO. What is the reaction? Otherwise, no reaction. That is reaction. APO. What is that? What is the reaction associated with that?
AP plus half or 2 is it?
APO. Formation reaction. Sir, formation reaction. 1 mole, sir. no other thing, sir. I remember only 1 mole of the product. Okay. Likewise, AP3O4. Similarly, sir, these are given in your data. I can see here it is given. I didn't write here. AP plus updated. So delta G is delta G0 because they are all solids and pure solids, obviously. Yes. So what is this? Write this. Write this by all means. And what is the T coming out as 62.67 is what you know, 575 degrees centigrade. This comes as 840 Kelvin. 840 Kelvin. What is the name of this in centigrade? Minus 567. Actually, I often consider 575 degrees, but this as per calculation. 5. So, what is your comment now? Take the comment. So, all three exist. But question is, iron will be in one of them. Iron will be at which? Given in one of the oxides at high temperature and another at low temperature. So, room temperature, so at T, tell me, at T greater than, so take up one by one, greater than this gentleman. Here delta G is 0, delta G at T greater than 840 Kelvin. What will happen to delta G is delta G0 is what? What will happen? Tell me. Is it greater than? See, negative. Negative means there now reaction will flow. Is it flow? Equals, and it will flow to this. What will produce? What will produce? Producing and APO will be a reaction will move in the direction, and the reaction will be spontaneous in the direction. Tell me. In the direction, tell me. AP3O4 2. I am giving one arrow. Direction to AP3 plus AP to APO. So what is the product? Easy. Problem has been over. Your answer is all given here. What temperature? This is the answer. Over. But try to understand. So tell me, what is the product? You see so many things into this. Okay. What is the product then? This is moving. Temperature is sustained above this, and it is moving until it will be, but this three cannot be together anymore. So they will spend.
Limiting the reagent is possible.
And the reactants are all done. APO alone. But there are some conditions. APO is must. No one can stop. So APO will be stable. At T greater than you can answer the APO must be, but with iron asked. Then what? Now tell me. When it is APO though? This is tacit. That AP3O4 and when, sir? If you are intelligent, okay, more intelligent, then you would say, sir, if these two were stoichiometric, sir. Exactly. One mole you have taken. Then they will go together. Suppose this is excess, then of course AP3O4 will gone, APO will be there. So this is this direction. So when AP, but since the question is asked with iron, means it is said that APO guarantees that AP is there in excess. So when AP is excess, and that is the question. So So 3 things are coming. Follow me. Total 4 things I will, and it will actually totally clarify everything, and then I will give you a nice diagram, and this will be 100% satisfaction. So when AP is, since the question is about AP, since AP must be present, with iron, question as per the question must be present. As per the question means, says with iron, question asking with iron means I am giving iron. Iron is given. With iron who? They will say as per the question. Sorry. So what are the phases? If AP must be present, that is AP is stoichiometrically in excess relative to, with respect to, I am writing many things with respect to AP3O4. Then what is the final product? Tell me, what is the final product then? Then the product is only the reaction is spontaneous. The reaction, since AP must be present as per the question, see, that is AP is stoichiometric excess of the final equilibrium product will be what? Tell me. So this is the iron who? APs are, APOs are. So will be APO, of course, mass plus excess. Acha, this is okay to? Over? Acha, is okay. Together then? Acha, I'll consider, let me complete this. Additional note here. At this case, together than 840. Note in passing, then you have understand that this is not the question. In passing, what? If AP3O4 is in excess, possible. In passing means this is not given. If AP3O4, tell me, if AP3O4 in excess, right. If AP3O4 is in excess, relative to whom? With respect to AP. Good. Reactant that in excess, then of course the equilibrium product will be, tell me, what? He is actually following very nicely. Are you going back to the classes, to your lectures? People coming, or sometimes you look back, okay? Maybe I'll take an exam. Will be very nice. Will be someone who should respond actually, other, then I'll be encouraged. Then the equilibrium will be very nice. That is APO mass, sir. This you follow, sir. APO, no one can say APO plus. The third question I will ask anyone else other than Unurag. APO plus, AP3O4. Then what option remains? I say from here to here, what option remains? Still here, 842, 840 Kelvin, greater than. What option remains? What one option? This option was asked. This is actually our discussion in passing. What option are the?
In amount of
Stoichiometric, not excess. Then yes, complete this. Yes, stoichiometric, sir. There is stoichiometric, means 1:1. You know what is stoichiometric? 1 mole of iron, 1 mole of AP3O, means 56 gram of iron. AP3O how much? It is 53 into 168 or 64, 232 gram. So there is 56 gram and 230. That is stoichiometric. Excess, 232. It is 70. It is excess. It is 56. It is 280. Such. No problem though. Complete that. Yes, stoichiometric. Then exact stoichiometric, no excess. Then very good. This is our understanding. So you understood everything, but you answer the question, but you know more than that. What is asked? Total picture. So that is now and also note. I do not know how long I will keep on saying note and note. Further note. In addition, note. Also note if AP Right, nicely. Ap and Ap3O4 means the reactants. Ap and Ap3O4, if Ap and Ap3O4 are in exact stoichiometry, are in stoichiometric amounts, are in exact means exact. Exact is redundant though. Stoichiometric is in exact stoichiometric amount. Stoichiometric ratio, stoichiometric amount. In stoichiometry follows the stoichiometry many way you express. Good boy. What is the product? FeO alone. FeO alone. FeO must. FeO must. FeO alone will be the equilibrium product. This is all about T. What? All about T848. These are the three cases right here. Note. So these are the three possibilities. Abilities at T greater than 842. But one possibility is asked. I am talking three, but first one is asked. Iron excess. Tacit is what? With iron. Oh, iron excess. Next, at three options. Fourth, I am giving. At very easy. You answer. Any of you? Be prepared. Any of you? Less than. Greater than. Less than means that covers room temperature. What will happen? Yes, the bomb, since you are looks like prompt. Less than, what will happen? See the reaction and then.
It will not take
Take place means who will be present? Then nothing. These two gentlemen. So who will be present with iron? Ap3O4, other oxide. So at Ap3O4 plus Ap, right? This way first will be the equilibrium product. Will be the, see, right. This better. Right, what to write again? Delta G is delta G0. I always write this. Is what? Positive. Positive to nakire. T less than my negative, decreasing. Positive. Hence, no reaction. First write that. Oh, no reaction will occur. And write this. And Fe, what is this? Ap3O4 plus Fe will be the equilibrium product. Product or equilibrium? Equilibrium. Okay, species sets, equilibrium product. At equilibrium product. Okay, equilibrium will exist at equilibrium. Will exist at equilibrium. Okay, equilibrium product. Don't worry. Equilibrium product. No reaction is not there, so no product. The reactant. Okay, equilibrium product or equilibrium the. Achha, question is 3. Is okay though? Is okay. Okay, very good. T less than equilibrium product. No reaction will occur and everything will remain. So in brief, what shall I? If there is okay. So answer the question. So in brief, what is your answer? So answers. So the answers is what? The answer is what? What? Determine which of these two oxides. Your answer is which oxides are in equilibrium with iron room temperature. So at room temperature, so the answer is at that at room temperature. What is that temperature? 298 Kelvin perhaps. 298 Kelvin to the warmer days. Okay, at room temperature, who will be present at room temperature? At less than Ap3O4, FeO. Which of these oxides in equilibrium with iron? So Ap3O4 will be in equilibrium with iron. Ap3O4 will be in equilibrium. The way it has will be in in equilibrium with iron. Answer. And what is the question next? And the maximum temperature is, tell me, guess. And the maximum temperature, tell me, maximum temperature is what temperature? That's right. The moment it crosses that, it will never be. At 840, can Ap3O4 will be? Yeah, yes, sir. 3, all Ap3O4 included. Beyond gone, sir. Maximum temperature is of such coexistence, right, is 840. You see this? Coexistence? Acha. Is okay? Acha, ठीक है. Is okay. And the cross. Sorry, it's almost done. And I don't want to disturb anything here. Sorry. And the maximum temperature, I'm writing here. And the maximum, okay, on screen too. Okay, yeah, visible. Maximum temperature is, and the maximum temperature is right here, of such existence, of such, what I wrote, of such coexistence, naki de? Coexistence is 840 Kelvin. Answer. You say that I have answered, sir. Kelvin. These two make the answer. It's okay. See, you can see this though. No, he can. Yes. Bus over. But just 1 minute. This is 100. This is 90% satisfaction. But even okay. I'm removing this part. See, thermodynamics is such a interesting subject. Mainly different ways you learn. I'm drawing this stability diagram. Try to okay, verify the above findings, previous findings with the help of stability diagram, with the help of a iron oxygen, with the help of a stability diagram, okay, of a stability diagram. Quickly, this is very, I'm drawing this, what I'm writing, stability diagram, iron, carbon, oxygen, the 3 component, right? Percentage CO in CO2 mixture. You are plotting against temperature. Have you drawn this figure, or have you come across this figure? Please tell me. Sorry, sir. Oh, sorry, sir. Have you?
Yes.
Very good. Then that will help me. Okay. This is the stability field for FeO. This is the stability field for iron. This is the stability field for Fe3O4. And I am giving you, in additional, though not involved here, but that is not bad to consider. A narrow region though. The Fe2O3. Stability field for Fe2O3. Fe2O3. Just in case you want to know, sir, what is this? This is the curve where FeFeO coexist. Coming back to this. this is the curve where AP, AP3O4 coexist. This is the curve where AP3O4, APO coexist. And this is the curve where, tell me, this is what? AP, the hematite. AP2O3, AP3O. Means above this line, AP3O4. Below this line, AP2O3. Just check this. Check this. Check this. What is represent on CO2 coming where? It is what is this curve? This is a stability diagram. Curve is this equation represents the equilibrium of what one I am showing. CO involves CO2. This is if you have time, I will teach you how to construct. You can draw yourself. That is the idea. What is the line? Which equilibrium? APO plus APO AP with CO goes to AP plus this equilibrium. You have drawn, and this is obviously another equilibrium. What is this? Similarly, AP3O4. I'm writing here. Don't worry this part. I'm similarly others. Okay. Now you clearly see what is this temperature? What is this temperature? Shall I write here? Since I was writing, since you are interested, looks like AP3O4 plus CO is 3 APO plus CO2. And what is this? What is this? What is this? What equilibrium? This one? AP3O4 AP. No, AP3O4 AP. A moment ago you said AP3O4 AP may be together. AP3O4 plus CO is what? 3 Fe plus 4 CO2 means 4 CO. Okay, this can be written one more. Okay, don't worry. Okay, so whatever. So this equilibrium. So this is a stability diagram construction I will not discuss, but you just check whether you are correct. Show me one by one. 4 cases. 4 cases. Can you show me 4 cases where? One is see, iron APO coexist. APO. This curve. This curve is what? Tell me. This curve is what? AP3O4, APO. Good boy. What is this curve like? AP3O4. Good. Very good. So tell me 3 options are there. So what is this? What is this temperature? Tell me what is this temperature? Yes. Where APO, AP2 coexist? 840 K. 840 Kelvin, which is actual force 70 degree for 67. Okay. So check at any temperature. What is the first one? Getter option. See, check getter option. What is possible, sir? 3 possibilities. One is what? APO alone. Another is open, sir. APO AP. Still another is APO AP3. Happy? Stoichiometric. And another below is what? Room temperature included. Is what, sir? AP3O4 AP. All matching. This diagram is consistent. Now I tell you, this is very important. One good question may be asked. You are reducing iron oxide AP2O3 at 900 Kelvin. So what are the stages of reduction? Reduction, it is not one stage. Several stages of reduction. So what is the stage of reduction? Just I am not showing. What is the stage of reduction? Tell me. I am showing. I am drawing. This is the question. Your Bhai Babos, your interview, you asked at 900 Kelvin, you are reducing. What are the stages? First AP2O3 is the beginning, hematite. Then it becomes AP3O4. Stability will have written clearly. Stability will clearly. You will encircle it. This is a stability field. This is a stability field. This is a stability field. This is the stability field of AP2O3. Oh, this also I write. What is this line stands for? What is this line? AP2O3. Shall I write here? Achha, this is no longer useful. Remove this. Remove this. This line I am showing here. What is the reaction? Right? AP2O3. Many books you will not get this line. This is almost merging with the x-axis. That's why you don't see. But to have the complete picture, AP2O3, guess, plus CO goes to guess, plus CO2. So it is 3 AP2O3, 2 AP3O4. You are all set. All equilibrium I have given. Okay. Percentage CO. All over. So 3 you have already answered. This 4 all answered. What question then I wanted to ask you? 3 already. 1, 2, 3. Oh, question was at temperature 900 Kelvin, for example, you want to reduce. What are the different product that will be produced in succession? What are the different stages of reduction? Ap2O3 starting. What it will next? Next, this way. What is this field? Ap3O4. This is APO. This is AP. Acha. Below this, any temperature below this is what temperature? 5. What temperature? 567. Na? 567 degrees centigrade. Below this, suppose this. What are the stages of reduction? Tell me.
Ap2O3, Ap2O4,
So that is the question. APO will not be stable this side. So it is not always APO. So this is actually critical question. So it will be Ap2O3. And then tell me, what is the how many equilibrium this is? How many phases are here? This line. This study this one of them. Study this. What does it mean? APO solid or the gas phase. That's the gas phase showing on the y-axis. So 3 phases, etc. Then there is actually phasal application. I will not take up this one. This one. Only thing along this line, who present? Along this curve, who present? Together. Who are together? APO I have written here. But above this line, who? Only APO and below APO. Thank you so much. With this, actually, we have solved the problem. Okay, happy to. Assignment 7 at least, I hope successfully completed. That's the next chapter. Okay. Okay. So can I remove this? Okay, all writings. Okay. Assignments. Right here, assignment 7 completed. These are right somewhere. Sorry. So assignment number 7 completed. So let us take up new chapter. Okay, phase equilibria. How much time there?
It is now 147.
That's right. Phase equilibria. And add here Clausius-Clapeyron equation. Clausius-Clapeyron equation. So assignment 7 complete. I am removing this. This all over. A clean set. Start. Quickly consider this. We are considering phase equilibria for right here. For phase equilibria for single component system. Or single component system. Process steps quickly. So this is actually, for example, I'm drawing you. If you have a picture, you are motivated. That's why I'm giving the answer at the beginning. But we will develop ourselves. Okay, this is a stability diagram I'm drawing. This is a phase diagram is a stability diagram, thermodynamic stability diagram. P versus T. This is the better. This should be curved one. I don't think is. Sorry, I missed actually. As a skidding, this one skidding actually. So anyway, so this is what solid. So I'm discussing iron, metallurgist. Solid iron. This is liquid iron. This is what? Vapor iron. vapor phase. Again, same story, solid liquid coexisting, and the left side solid alone, etc. Here liquid vapor and solid vapor as is possible. So what is this actually? Consider, this is the figure 1, given name, it is better. Figure 1. So figure 1 is the stability diagram, okay, is the phase diagram, which is also stability diagram for a single component system, it's A for iron, A can represent iron, A say system for a single component system. This is the phase diagram. We are going to develop the equations so that we can draw ourselves. I'm writing so many things. This is not written in here. So I'm giving you confidence. I'm actually trying to, okay, this infuse confidence. We are going to find the equations OA. This is a triple point given name. A prime I'm thinking because A I will use somewhere already used. This is A. So A prime better, and your A prime, sir, OA prime, solid liquid, OB prime, OB prime, OC prime. We are going to find the equations for OA prime, OB prime, and OC prime. So that I am writing this additional, so that we may draw. In fact, if I get time and if you give time, stability, I will see how to construct these diagrams. Okay, from OA, OB prime, so that we may draw the diagram ourselves. With the data also, draw the diagram ourselves. This I am writing, so to give you confidence. Start. Consider the first take up one by one. Quickly, let us, not much time. First take up equilibrium, solid liquid equilibrium. Solid liquid, consider take up the equilibrium, solid liquid. Solid to liquid, that is the curve which is represented by tell me, which is represented by curve, tell me, curve, OA prime. So OA prime equation starting is this. So what is the equilibrium? A solid goes to A is the single component, A liquid, this is the equilibrium. Okay, explicitly, A solid to A liquid. So at a temperature Tp, what is this about? OA prime, OB prime, or is about Tp relation, pressure temperature relationship. Remember, we can find the equations, that is right here, T versus P relation, then that is the equation. So it is readable. Note that for OA, which is note the three curves. Note the three curves. Note the three curves represent the curves give the three curves. Three curves are obtained from the corresponding corresponding TP relation. Corresponding TP relation. This is actually you are trying to get the TP relation for 3 solid to liquid. First consider. So OA, it is giving this, okay. Now temperature, pressure. So at a given temperature, I just see follow. Equilibrium to where, sir? This is the point. So at a given pressure, temperature. Okay. There is something about degree of freedom, but this at the end. Okay. Pressure, temperature may be different. So, by the way, another point note. Another point note. What is this? Sorry. Another point note here. What is this? OA prime is what? Solid liquid coexistence. That is called melting point. So it is actually the locus of melting points. But the melting point is, how many melting points are there? Sir, infinite number of melting points. What is this? What is this called? This liquid vapor coexist where? Boiling point. And there are infinite number of boiling points. Similarly, solid vapor exists at where? Sublimation points. Infinite number. How many points are there? Infinite number. This is equilibrium, this is equilibrium. Infinite. TP combination. Infinite temperature pressure combination. If this is the pressure, this is the temperature. This is the pressure, this is the temperature. Infinite combinations. Then one we are particularly concerned or more concerned and often use, what is that? Normal melting point, normal boiling point, and normal sublimation point. Normal boiling point is what? The melting point corresponding to P is 1 atmosphere. It's pressure value. That is normal. Pressure 1 atmosphere is the superincumbent pressure. So that means when it is 1, this melting point is called normal melting point. Other melting points are possible. So you make your mind free from any confusion that infinite melting points. Only one of them is called normal melting point. Similarly, normal boiling point is what? The boiling point corresponding to P is 1 atmosphere, and likewise sublimation. Okay, so these are the few things that actually I didn't write though. But start I'm writing at TP. If you say what is TP, sir? Any TP? All points are TP, sir. Generally represented. T is the temperature. At TP, delta G is what? Delta G is equilibrium. I have written consider the at equilibrium. Since they are at TP, at equilibrium, the coexist. I am trying to get the equilibrium curve, solid liquid equilibrium curve, which is OA prime. And that's why I need to get the TP relationship. There are so many T and so many P's, corresponding P's. So delta G is how much? Delta G is how much? At TP, what is the delta G? At TP they are in equilibrium. What is the delta G? 0. Equilibrium delta G is 0. Delta G, I asked, you thought I asked you to find the delta G. You are thinking in the delta G is delta G0 plus RT ln Q or VdP minus SdT. All kinds of things are. So I have ln V2 by V1. So who knows? Delta G 0. That leads to what? Ga liquid is Ga solid. Acha, a example of a right here. A I have considered a example for a little better. I have A is what? Single